So 4.5, we're going to be talking about curve sketching. So basically the idea is we're going to be using calculus to help us graph things. So in this sheet that we have, there is a summary of a whole bunch of different things that we're going to do. So our guidelines for curve sketching are as follows. So we're going to take some of the things that we've done in our previous sections. So first thing we always want to do is find the domain of the function in question, and then we want to look for any intercepts for our function, so any x-intercepts and any y-intercepts. Step C is optional, but it is often helpful if a graph has symmetry, and we'll see this again a little bit later in chapter 5, that certain symmetries are very nice, so we can test if a function is even, odd, or periodic, and we'll remind ourselves how to do that in a bit. And then test for horizontal asymptotes, and so we're going to take some limits. We take the limit as x goes to both positive and negative infinity. Vertical asymptotes, and we get those by finding zeros of the denominator and testing one-sided limits. Intervals of increase and decrease, we're going to use our first derivative test for that. So our function is increasing if the first derivative is positive, and it is decreasing if the first derivative is negative. And then G, we want to find local maximums and minimum values and use the first or second derivative test to find those local maxes and mins. All right, if we keep going, there's a couple more things on our list. We can test for concavity, and then finally we can use calculus to help us find all of these points and then summarize basically all of the important points that we have on our graph. Okay, so basically we're going to do an example where we're going to try and do each of these things for our function, and then we want to graph this thing. So we want to graph f of x equals 4x cubed plus 7x squared minus 10x plus 1. So the first thing on our giant list of stuff is we want to find its domain. So our function f of x is a polynomial, so its domain is going to be all real numbers. So the domain of a polynomial is all real numbers. And then our second thing we want to do is find any of the intercepts. So then find our x-intercepts. We're going to set f of x equal to 0 and solve. So that gives us 4x cubed plus 7x squared minus 10x plus 1 is equal. So we have a theorem from way back, and our theorem is if P is a rational solution to a polynomial, well, let's not use P. Let's use C. And I'm going to need P in a second. So if C is a rational solution to a polynomial, then it has the form P divided by Q, where P is a factor of the leading term, and Q is a factor of the constant. So I know that's not super clear right now, but in our case, what that's saying is that our P is going to be 4. And then our constant in this polynomial is 1, so q equals to 1. So then if we have a 0, it has to be of the form p divided by q. Well, the only factors of 4 are 4, 2, and 1. So our only possible zeros are plus or minus 4, plus or minus 2, or plus or minus 1. And if we checked those in our original function that we have here, we would see that none of those are going to be equal to 0. So let's go ahead and just do that really quick. There we go, 4x cubed plus 7x squared minus 10x plus 1 then if we just make our table, we can see that at 1, and then all I wanted to do was show that if we make a table of values, if you look at 1 and negative 1, they're not 0. If you look at 2 and negative 2, they're not 0. And if you look at 4 and negative 4, they're not 0. We could have checked them all manually by putting them in. It's just that would take a really long time. So that just shows us that this does not have any zeros. So turns out this polynomial doesn't have any rational zeros, which sometimes they do, sometimes they don't. If we're more concerned about that when we'll talk about how we find these a little bit later on, and it's something called Newton's method, but for right now we're just going to go with this. All right, the next thing we want to take a look at is that. There we go. The next thing we want to take a look at is, so we found our intercepts. Oh, we're almost done. Almost done. So that was the x-intercept. So how would we find the y-intercept? So for these ones, we set x equal to 0. So we're just going to plug that in. So if we plug in 0, that's going to give us 4 times 0 cubed plus 7 times 0 squared minus 10 times 0 plus 1. And so basically everything but the constant term is equal to 0. And that is going to give us 1. All right, so then the next thing we want to test for is symmetry. And when we want to test for symmetry, once again, we got to jump in our way back machine to pre-calc or so. So if a graph is symmetric with respect to the y-axis, what is true? So for y-axis symmetry, we have that f of negative x is equal to f of x. So basically, if we replace x with negative x, do we get the same thing? And what was the other name for y-axis symmetry? So this is the same as an odd function. So if we replace x with negative x, we're going to have f of negative x is equal to 4 times negative x cubed plus 7 times negative x squared minus 10 times negative x plus 1. And if we have a negative x times negative x times negative x, that gives us a negative, so we get negative 4x cubed. Negative times a negative, and negative x squared is positive, so we get positive 7x squared. Negative 10x times negative x is positive 10x plus 1. And then this does not equal to f of x because it's got some missing or different sign terms than the original function. So this one is not even. Wow. All right, I get an F. We're going to go back. So y-axis symmetry isn't odd. That is even. So, all right. This really should have been an even function. So y-axis symmetry is exactly the same as an even function. All right, so this is not even. So then our next symmetry is symmetry with respect to the origin. And symmetry with respect to the origin, this is the odd function, so aka an odd function. And this symmetry is that f of negative x is equal to the negative of f of x. So we already calculated what f of negative x was, and that was right here. So now the question is this the same as negative f of x? And the answer once again is no. So then this does not equal negative f of x, so it's not odd. So this graph has no symmetry. All right, so moving along in our list so far, the next thing we would need to find are our horizontal asymptotes. So once again, with a polynomial, we need to take our limits as x goes to positive and negative infinity. But if I take the limit as x goes to positive infinity of our original function here, so we would have 4x cubed plus 7x squared minus 10x plus 1. What's that limit going to be? Well, which of these terms is going to dominate? Well, that's going to be this one. So as we go to positive infinity, we're just going to get positive infinity. So we're not going to get a horizontal asymptote there. And if we do the same thing, we take the limit as x goes to negative infinity of 4x cubed plus 7x squared minus 10x plus 1. This time, negative infinity times negative infinity times negative infinity is going to give us negative infinity. So we have no horizontal asymptotes, but the fact that we have these two things tells us something. So as x goes to positive infinity, our graph goes to positive infinity. And as x goes to negative infinity, our graph goes to negative infinity. So then this tells us what our end behavior is, which means it's going to start down, wiggle in the middle, and it's going to end up. All right, so now, next thing on our giant list of things we need to do is find a vertical asymptote. Well, polynomials are not going to have vertical asymptotes because we are never going to divide by 0. So this one has none. We'll normally find our vertical asymptotes on rational functions or on logarithms. So now F says find our intervals of increasing and decreasing. So our intervals of increasing and decreasing are going to be found by using our first derivative test. So we take our derivative, so the derivative f prime is going to be 12x squared plus 14x take away 10. So now we need to find our critical numbers. So our critical numbers are found by setting the derivative equal to 0. So that gives us 12x squared plus 14x take away 10 is equal to 0. And now let's go ahead and try to factor this. So the first thing we notice is we have a GCF of 2, and that gives us 6x squared plus 7x take away 5 is equal to 0. And then we can either use the quadratic formula or try to factor this, but if we go 6 times negative 5 gives us negative 30, and we need factors of negative 30 that give us 7, and that's going to be positive 10 and negative 3. So if we split up our middle term here and rewrite it as positive 10x take away 3x minus 5 is equal to 0, we get this, and we're going to factor by grouping. So we factor out our GCF out of our first term, which is 2x, leaving behind a 3x plus 5. And then our GCF in the second two terms is negative 1, and that leaves behind a 3x plus 5 as well. So then we factor out our common factor of 3x plus 5, and we get 2 times 3x plus 5 times 2x take away 1 is equal to 0. So finally, that gives us our critical numbers, which are negative 5/3 and 1/2. So to do our first derivative test, we're going to make our number line, and we label our critical numbers, so negative 5/3 and 1/2, and then we need to just test a point in each of those regions. So if we test something less than negative 5/3, so that would be like negative 2, we could just put it in our calculator or just do it right here. So if this is positive, so it's not going to matter. 3 times negative 2 is negative 6. Negative 6 plus 5 is negative 1, so this first factor is going to be negative. And if we plug a negative 2 in here, 2 times negative 2 is negative 4. Take away 1 is negative 5. So a negative times a negative gives us a positive. And then we need something between negative 5/3 and 1/2. So that's 0. If I put 0 in for this, well, that's easy because anything times 0 is 0. So 2 times 5 times negative 1 is going to give us a negative. So that means it's negative, and if we test 1, 3 times 1 is 3, 3 plus 5 is 8, 2 times 1 is 2, 2 take away 1 is 1, so 1 times 8 times 2 is positive. So we get positive, negative, positive, so that means our graph is increasing, then it changes to decreasing, and then changes to increasing.
Professor Peterson?
Yes.
Were you just plugging that back into the factor right there?
Yeah, I was plugging it into this, but if you wanted to, you could plug it back into f prime. It just needs to go into f prime. So just to be explicit, if we really wanted to, we could just put these values into the derivative. It's just, since we only care about the sign, it was a little bit easier to do it in your head by just counting the signs in the factored version. But if we do it here, like on the calculator, so if we go down here and check now, let me pull this back up. What we were doing is we put in like negative 2, right? So we go alpha trace, we grab this, and we go negative 2. And we got positive 10, which told us it was positive in this region. And if I put negative 2 into this factored version right here, we had 3 times negative 2 is negative 6 plus 5 is negative 1, and then we had 2 times negative 2 is negative 4, minus 1 is negative 5, so I had negative 5, negative 1, and 2, so that gives us negative 5 times negative 1 is positive 5 times 2 is 10, which is the same value we got on the calculator. So you can do them this way, plug them into the derivative, plug them into the factored one, and it doesn't matter. We'll get the same number regardless, as long as we're plugging it into the derivative. All right, did that get your question?
Yes, thank you.
Okay, perfect. So then we went from increasing to decreasing, so then that's going to be a max, and then we went from decreasing to increasing, so that's going to be a min. So then that tells us that our function is going to be increasing from negative infinity to negative 5/3, unioned with, and then it increases again from 1/2 to positive infinity. And then we're going to be decreasing from negative 5/3 to positive 1/2. So those are our intervals of increasing and decreasing. And the next one is to find all local maxes and local mins, and we actually just did that. So we have our, or at least the inputs, so our local max is going to be at x equals negative 5/3, but then we need to find the corresponding y value, and that is going to be at f of negative 5/3. So we need to plug 5/3 back into the original function. So that was the original f all the way back at the beginning, right? So if we put in our negative 5/3, or if we just put this function into our calculator, we would have 4x cubed plus 7x squared minus 10x plus 1. And we want to put in negative 5/3, so alpha trace. And we have our negative 5/3. And that gives us 502 over 27. And then to find our local min, we're going to rinse and repeat, but this time we're going to use x equals, and our min was at 1/2. So then the corresponding y value is f of 1/2. And we get negative 7 over 4. So then we have our max at negative 5/3, 502 over 27, and we have our min at 1/2 and negative 7 over 4. And just because it'll be helpful a little bit later, I'm going to get an approximation of 502 over 27, and so that's about 18.59. So I'm going to go with 18.6-ish. And this guy is going to be about negative 1.75. We're going to draw a graph later. All right, so let's see. Going back to our list, let's see, we did increasing, decreasing, local maxes, and local mins. Oh, we're finally at the end. H, we want to find concavity. and inflection points, and then the next one is we want to sketch the curve. So to find the concavity, we need to find our inflection points, which are the zeros of the second derivative. So we take the derivative of our derivative. So our derivative is 12x squared plus 14x minus 10. So that's going to give us 24x plus 14. And then now we set that equal to 0. So we have 24x plus 14 is equal to 0. And we minus 14, minus 14. 24x equals negative 14. Divide by 24. Divide by 24, and that gives us x equals negative, and let's see, 14 over 24 reduces to 7 over 12. So that's the 0 of our second derivative. So using our number line, once again, we have negative 7/12, and we just need to check the sign of the second derivative. So something less than negative 7/12, so let's check negative 1. If I put negative 1 into f double prime, so f double prime of negative 1 is 24 times negative 1 plus 14, which is negative 24 plus 14 equals negative 10. So that's negative. And if we check something bigger than negative 7/12, we do f double prime is 0, and that one's easy because 0 times anything is 0. So we just get 14, so it's positive. So then that tells us that our graph is concave down on this side. And since it's positive over here, our graph's going to be happy, and it's going to be concave up. All right, and our inflection point is going to be at negative 7 over 12. So to find our inflection point, we're going to do the same thing we did when we were finding the maxes and the mins. We're going to take our x value of negative 7 over 12, but we have to put it back into the original function. So that's already in our calculator. So we then just go alpha trace, choose y1, and we're going to put in negative 7 over 12, and we get our corresponding y value of 1,819 over 216. Oh, let's actually approximate that before I clip. 1819 over 216. So that gives us our inflection point is at negative 7/12, comma 1819 over 216, and we have that is about 8.4-ish. All right, and then lastly, we need our concavity. So let's see. It was concave down from negative infinity to negative 7 over 12. And then it's going to be concave up from negative 7 over 12 to positive infinity. All right. So now finally, we want to graph this entire thing. So let's go ahead and put some of our important points that we have on here. So we had our local maxes and our local mins. So our local max was at negative 5/3, so this is like negative 1.66 and 18.6. And that's going to be our local max. And then we had our local min is going to be at 1/2 and negative 1.75. And that's going to be our min. And then we had a couple of other points. So our graph had its inflection point at negative 7/12. So that's going to be like negative 1/2-ish. And 8.4. That's our inflection point. And then we knew it was increasing till it hits its max, then it decreases, and so forth. So our graph's going to look something like this. Oh, it's going to go up, and then it... I'm terrible. Let's see if I can draw a better picture, because it's got to be concave up, and then it switches to concave down, that point, and then it turns around and it comes back up. It looks something like this. Alright, that's terrible though. We get the idea. And so we have, with calculus, we were able to find the max, the min, and where our graph changed from being concave up to concave down. And just to remind us, what does it mean to be concave up and concave down? So when the graph is concave down, to help you when you're drawing it, remember it has to lie below all of its tangent lines. And on the part where it's concave up, it has to lie above all of its tangent lines. So it just helps you know kind of the curvature of what that graph is going to look like. So now, since I'm terrible at drawing, let's press graph. And then we have our calculator, and then let's change our window to match. So the x's are fine, but let's make our y min negative 5, and let's make our y max 20. And we press graph once again. And there's a little smoother, but indeed we have the basic idea of what that graph looked like when we did this. All right, so let's take a look at our next example. So the next one says, find the oblique or the slant asymptote of f of x. So this is another one of those things we've got to remember how we do this from pre-calculus or some other class. So to find an oblique asymptote of a function, we use polynomial long division. So one thing we have to remember is if a polynomial is missing any terms, we must fill them in with 0x to the n. So the reason I mention this is if we look at our first polynomial here, we have our p of x in the numerator is x squared minus 4. It's got a second degree term and it's got a constant term, but it is missing the linear term. So before we can do polynomial long division, we need to rewrite p of x as x squared plus 0x take away 4. So adding 0 times x, well, 0 times x is 0, and adding 0 to something doesn't change it. So this is really the same polynomial that we started with. But if we're missing any terms, when we try to do polynomial long division, things are not going to work out quite the way we would like. And what I mean by that is that our columns won't line up properly when we do long division. So to do long division, we set it up just like we would if we were dividing two integers. And we start by trying to divide x into x squared. So the easier question to ask yourself is, well, what times x is going to give me x squared? So x times x gives me x squared. So I put my x up here, and then I go x times x is x squared, and x times negative 4 is negative 4x. Then the next thing I would do is I need to subtract. So just as a reminder, if I was trying to do 5 into 127, this algorithm that we're doing is exactly the same as this. So 5 goes into 12 twice. Then the next thing I do is I take 2 times 5, and that gives me 10. And then after I get my 10 down there, I subtract those. So 12 take away 10 gives me 2. And then I bring down my 7. So we did the same thing. We found out our x. X times x is x squared. X times negative 4 is negative 4x. Then we have to be careful, though, because we're subtracting that whole binomial, so it goes in parentheses. So then x squared minus x squared, those guys reduce out as they're supposed to. But now I have 0x minus a minus 4x, so minus minus makes it positive. So 0x plus 4x gives me 4x, and then we bring down our next piece, and we rinse and repeat just like we would over here. So 5 goes into 27 5 times. 5 times 5 is 25. We subtract, we get 2, and then finally 5 doesn't go into 2, so we just say we have a remainder 2. So now back to our polynomial long division. Well, what times x gives us 4x? Well, that's going to be 4. So we have 4 times x is 4x. 4 times negative 4 gives us negative 16. We subtract. Those are going to reduce out, and I have negative 4 minus a minus 16. So negative 4 plus 16 gives me 12, and that's going to be my remainder. So then the oblique asymptote is the whole part without the remainder. So our whole part here is x plus 4. So then that gives us that our oblique asymptote is y equals x plus 4. Well, why is it that our oblique asymptote is y equals x plus 4? Well, let's use the analogy that we had over here. So we had 5 into 127. Well, that says 127 over 5 was 25. That's our whole part, plus our remainder, 2 over our divisor of 5. Well, this says, if we look at it in terms of like being a mixed number, that 127 over 5 is about the same as 25, as long as this part is small. Well, let's write out what our polynomial long division said. So we had x squared minus 4 all over x minus 4, and that was equal to our whole part, which is x plus 4, plus our remainder, which is 12, over our divisor, which is x minus 4. Well, if we took the limit as x goes to infinity of both sides of this, we're going to end up with the following. The limit as x goes to infinity of x plus 4, plus, I'm going to break this up into two limits, the limit as x goes to infinity of 12 over x minus 4. Well, this piece right here, the value of that limit is going to be, well, we have a constant divided by infinity, so that thing's going to go to 0. So what this really tells us then is that the end behavior of these two things is the same. And what that really means, that as long as this remainder piece is small, so as long as x is getting really, really big, and in fact, as long as it's not close to 4, which is when it gets really, really big, the graph of this function is actually going to look a lot like the graph of this function. So let's go ahead and graph each of those and see what happens. So if we go and we type in our x squared minus 4 over x minus 4, oops, and then this guy should be x plus 4. So if we go zoom 6, because I messed up the window, there's our graph, and at first glance we see by 4 they don't look very much the same at all. Well, let's go ahead and change our window. So let's go from negative 100 to a positive 100, and let's scale in tens. Same thing here, negative 100, positive 100, and let's scale in tens. And when we do so, we notice something very, very interesting happens. As soon as we get outside of 10, that rational function looks almost identical to that line. So what the oblique asymptote is telling us is that that rational function behaves exactly like that line once we get away from its vertical asymptote, which occurs at x equals to 4. So